and the application, how it applies to torques, kinetic energy and the work energy theorem, and momentum, angular momentum. So there are ideas that we've seen already. Newton's second law, energy, and momentum are things that we've done. Now we're going to apply them in exactly the same way, except it's going to look a little bit different because now instead of moving in a straight line, we're now moving in a circle. And so we just deal with things a little bit differently now in this rotational frame. I will remind you that we've been making these translations from the linear to the rotational frame, where we've been changing our variables x, v, a, f, and m. We've been changing them to theta, omega, alpha, torque. It's not equal to torque, but it's analogous to torque, and then moment of inertia. And so we've already seen some equations that have been different. Like, for example, we had our kinematics equations, theta equals omega naught t plus 1/2 alpha t squared. Right? That looks a lot like our x equals vt plus 1/2 at squared. Today we're going to see another equation that is Newton's second law that we're now going to apply in a rotational frame. If you imagine that you have a disk that, say, rotates about this direction, about that axis, if I apply a force to it, that force is going to cause it to spin. It's like your steering wheel, right? You apply a force to it, and that makes it move in one direction or the other. Well, that force causes a torque, and the torque is what causes it to spin. And so torque is going to be equal to the moment of inertia times the angular acceleration. This looks a lot like Newton's second law. In fact, it is Newton's second law, right? F equals ma. Except I've replaced the F with a torque, or a tau. I've replaced mass, which is a measure of inertia, with moment of inertia, and I've replaced the acceleration with an angular acceleration. Okay, so we've done net torques, and now we're going to look at torques and how they cause motion, that they can cause an object to rotate with a certain angular acceleration. Let's go to the homework in the back of the chapter. There's a problem there that I want to work, and then we'll be able to do some in the back of the workbook in the old exams before you leave today. Okay, so this problem asks for the kinetic energy. Let's not worry about that right now. Let's first ask, what is the angular velocity of this object after it goes around for 3 seconds? What is the angular velocity after it rotates for 3 seconds with a force that's being applied to it? So let me draw a picture first. Angular velocity, by the way, that's omega, right? Be able in your mind to translate the words to the variables. It'll really help you a lot because you get the equation sheet, but if I ask for angular velocity and you don't know what that means, then you're going to be, in trouble. So let's draw a picture. This is a merry-go-round. This is from the top, and so it's rotating about that axis. Whenever you think merry-go-round, think, that's a disk. And when you think a disk, think, that's a cylinder. And on your equation sheet, you have these equation sheets I'll give you for your quiz today. You have this table that has all those rigid bodies. And so you look on there and you say, well, a disk is just a really flat cylinder, and the moment of inertia of a cylinder that rotates about that axis is 1/2 mr squared. 1/2 mr squared. Look, in these problems, you're always going to need the moment of inertia. So I usually just calculate it right out. So I'm going to do that here. The moment of inertia of this is going to be the mass. Oh, goodness. Look, I don't give you the mass. I give you the weight. And so the mass is going to be that divided by 10, or 80 kilograms. Remember, F equals m times g. So m is F over g, the force weight divided by 10. So it's going to be 1/2 of 80 kilograms. I think there was a problem on the exam, right, where I gave you weight, but you really needed the mass. Yeah. All right, 1/2 of 80 kilograms times the radius. The radius is 1.5 meters squared. And so that's going to give me my moment of inertia, 40 times 1.5 squared, 90. That's equal to 90 kilogram meters squared. Now, I want to know what is the angular velocity. I'm going to have several steps in this. I first have to find the torque, the net torque. This one's easy because there's just one force, and so there's one torque. I just have to find one torque. Then I have to find the angular acceleration, and then I can find the angular velocity. 3 steps, or really 4, because I've already done one of them. Find the moment of inertia, the net torque, the angular acceleration, and then the velocity. We've done problems like this. We did these back in chapter 4 when we were dealing with Newton's second law. So you've seen this before. It's just, it looks different because the variables are different. So this was step 1. Step 2 is to find the torque. It's Fr sine theta. F is applied at the edge of this merry-go-round, and F is equal to 50 newtons. So it's going to be 50 times R, which is 1.5. This is equal to R right here, 1.5 meters, times sine of theta, which is sine of 90. Because it says that it's applied tangentially, the force. That means that the force is applied at the edge like this, at a tangent to that circle, which is, that means that the angle then between the moment arm and the force is 90 degrees. So 50 times 1.5, that's equal to 75 Newton meters. Found the torque. Now that I have I and I have tau, I can find alpha, because I know torque equals I alpha. And so that's 75 is equal to 90 times alpha. .83 radians per second squared. Look, you will never go wrong with having your angles in radians. Sometimes I give them to you in revolutions per second or degrees per second. You'll never go wrong converting them to radians. Sometimes you'll go wrong if you don't convert them to radians. So if you're ever uncertain, then just convert them to radians. So for example, when you're working with the kinematics equations, doesn't really matter what the units are. Whatever units you put in, you'll get out. Likewise, when we're dealing with something called the conservation of angular momentum, you'll see later that it doesn't matter. But sometimes it does matter, and that in this case it matters here, that I have to use radians if I'm using SI units elsewhere. Anyway, I get out radians per second squared here. And then finally, the fourth part of this question is asking, what is the angular velocity after 3 seconds? At t equal 3 seconds, what is omega? And so omega is equal to omega naught plus alpha t. That is my angular velocity. It starts out at rest plus 0.83 radians per second squared times 3 seconds will give me 2.5 radians per second. That's not what this particular question was asking. It's actually asking for kinetic energy. But to find kinetic energy, we need the velocity. So we'll do that next. But you will have a question, 2 or 3 questions on the exam, where I ask you to do stuff like this, where you have to find the moment of inertia, find the net torque, find the angular acceleration, and then also find something with our kinematics equation, either omega or theta. Okay? You'll see those on every old exam. I always ask them. I'm going to ask you those questions too, a couple of times, 2 or 3 times. Now, that gets me to the next big idea, and that is the idea of kinetic energy. And I'll just sort of write some notes here about this. So you should go back and review the Chapter 8 notes if you haven't yet, and just get some more of the details about kinetic energy. Remember before we were dealing with kinetic energy, it was equal to 1/2 of m times v squared. Now, this is a translational kinetic energy, meaning that it's in a straight line, for an object moving in a straight line. The rotational kinetic energy, this is translational. Rotational is going to look really, really similar. But instead of mass, which is a measure of inertia, we're going to have moment of inertia. And instead of v, which is our velocity, we're going to have angular velocity, or 1/2 I omega squared. This equation is on your equation sheet. Just be familiar with it, know how to use it. In this case, I wanted to know what is the velocity of this object. So now there's just one more step that I need to do. Or, no, excuse me, not what is the velocity, what is the kinetic energy? Which is why I said, well, we really need the angular velocity, because now we're looking for the energy. And I know that my energy is proportional to that velocity squared. So my kinetic energy is going to be Ke equals 1/2 of 90 times 2.5 squared. Maybe 45. I got 280. Is that? Did I get 280? Yeah. So that's 280 joules. You'll need to find the kinetic energy of a rotating object for sure on the next exam, and it'll probably be in a line of questions that are kind of like this, where you have to first find the velocity and the moment of inertia and the net torque and the angular acceleration. Something else that comes up, we might have time today to work through a problem, we'll see. But there's another idea in chapter 5 related to energy, and that was the work energy theorem. If you recall, that work is equal to force times distance, or force times displacement, and that work causes a change in energy. And we look specifically at a change in kinetic energy. That's going to be true here too, that if I have an object acting, or if I have a force acting on an object like this, that causes some torque on that object because it's acting at some moment arm or lever arm on that object, that torque does work on the object. And if you can imagine, you know, F times D, you might be able to imagine an expression for work in a rotational frame. I'm just going to replace my force with torque and replace D with theta. So if this force acts over a certain angular displacement, say it acts over, I don't know, 2 pi radians, so that it goes through the entire circle, then it will do a certain amount of work on that object, increasing its kinetic energy. So the way I do that is I would say, well, F times R, that's my torque, times theta is going to be equal to 1/2 I omega squared. That's the work energy theorem. It's an idea that we've had before, that if I do work on an object, I increase its kinetic energy. And if I do that, then I can figure out things like what is the new speed? If it started out at rest, or if it started out at some initial energy, what is its new speed? We'll try to get a problem like that. I'm not sure that we will, but if not, we'll do it next time. Okay? Let's go to the next page. Remember, 3 big ideas. We've already seen one, Newton's second law. The second was kinetic energy, and then also the work energy theorem sort of wrapped up in that. And then the third is angular momentum. Remember, we just had a chapter on momentum that was on our test, right? Momentum. And when I have an object that's moving in a straight line, it has momentum. And that momentum is a product of the mass and velocity. The momentum is a vector quantity, although it wasn't really that important for us because we were dealing in 1 dimension. But it is a vector quantity. The same will hold true for rotating bodies, that a rotating body has momentum. It has angular momentum. And that angular momentum is going to be a product of its inertia, its moment of inertia, and its angular velocity. And just like with objects that were traveling in a straight line, see, I'll write this down here, where P is equal to mv. Now I'm going to have a new expression where L is equal to I omega. So this equation is translating into sort of its angular cousin, if you will, where I can calculate the angular momentum for an object. Notice that if the mass of an object goes up, the velocity goes down. Like you'll have that coal car problem on the test. See like that problem. All right, I like it. You have the coal car problem, and then you added mass to it. That meant that it slowed down, because as the mass went up, the velocity went down. That's true here too for rotating bodies. If you can will slow down. We see this a lot, right? Like with figure skaters or dancers or gymnasts or people that sort of use their bodies to express things like that. That they use their bodies in a way to change their moment of inertia. So for example, if a figure skater takes their arms and throws them out, what's that going to do to their moment of inertia? If they take your mass and move that in bigger radii, does the moment of inertia go up or down? Moment of inertia go up or down? It's going to increase, right? I is mr squared, so if r goes up, I also goes up by a lot, right? And then likewise, if that figure skater takes their arms and brings them in, that means the moment of inertia is going to go down. Okay? Because remember, moment of inertia is dependent not on the mass so much, because your mass can stay the same, but on how you distribute that mass within your coordinate system. So if I make I go up, what happens to omega? It's going to go down. There's an inverse relationship. So if my figure skater does this, will slow down a lot because she or he has now made their moment of inertia a lot bigger. And that's what this problem is getting at. This is actually an angular momentum problem from old days. If you have a rotating body like a galaxy or a star-forming region, those things are fed by gravity, and then gravity attracts masses to fall in. And it should be that as those masses fall in, just like the figure skater, they should spin faster. And it turns out, though, in star formation that if you account for how things fall in, that those bodies of gas and dust, that they really should just fly apart because they become unstable. And so that's long been a problem in star and galaxy formation. How do these bodies hold together? And the physical answer for that is magnetic fields and thermal forces are at play that hold those objects together as they coalesce and form bigger bodies. Anyway, this object is moving its masses from a distance of 1 meter to a distance of 0.5 meter. Describes this in the problem where the objects are connected and then they're shortened to 0.5 meters. So the objects are originally 1 meter from the center, and then they all move in. It's like having a bunch of kids on the merry-go-round, and all the kids are out on the edge of the merry-go-round, and then they move in. Have y'all ever done that before? You ever moved in on a spinning merry-go-round? Yeah, it makes you go faster, right? It's actually kind of difficult to move in on a spinning merry-go-round. It's just sort of, you have to pull yourself in, but it makes you go faster. And that should happen here. So, in order to figure this out, I have to consider the initial angular momentum and set that equal to the final angular momentum. Because just like with linear momentum, angular momentum is also conserved. The initial angular momentum is going to be I initial, omega initial. The final will be I final, omega final. And I'm looking for this quantity. What is the final speed? Omega initial is 2 revolutions per second. And I initial is going to be mr squared. So m times 1 squared, and there are 4 of those bodies. These are just discrete particles. I treat them as such. Times omega, which is 2 revolutions per second. Notice that I did not convert this to radians per second. When you're dealing with angular momentum, it's not necessary that whatever units I put in for omega, I'll get out for omega. And then this will equal to 4 times m times 0.5 squared. Because I've made the objects move in, they've collapsed towards one another, times our new omega final. So the m's cancel here. Notice they're not relevant. It's just the distribution of the mass that's relevant. And so that becomes 8 equals 1 times omega final. So omega final is just equal to 8 revolutions per second. And again, notice, whatever units I put in here, I get out here. That's not always true in rotational equations, but it is for angular momentum. Not for Newton's second law, not for kinetic energy, but yes for the kinematics equation and this angular momentum. You'll get the hang of that if you practice this a lot. You'll begin to see you get the hang of when you need conversions or not. Okay. Let's, first of all, any questions? We can work some problems in the back. Questions. Those are the three big ideas. Newton's second law, kinetic energy, and the work energy theorem, and then angular momentum and then conservation of angular momentum. Okay, by the way, I would say this, like when we're doing angular momentum, we said that F was equal to ddt. Similarly, F was delta P over delta T. In a similar way, you don't need this, but the torque is equal to delta L over delta T. That everything sort of fits in our rotational framework. Everything we saw in chapters 4, 5, and 6 will now fit into this chapter regarding Newton's second law, energies, and angular momentum. But you won't see that on the exam. That was sort of our impulse section that we talked about in chapter 6. Okay, let's go to the back of the book then. I think I was doing fall 17 earlier. Exam 4. Yeah, let's do this one. Fall, it says 207. That should be 2017. So let's do, I think this is the one I wanted. Yeah. Let's do 7 and 8. So I'm not going to put the clicker up for 7, but you have to start with 7. Really, the question that we're doing is number 8. This is fall 17, exam 4. Now I want you to try this number 8. This is a Newton's second law problem. I'm looking for the rod's angular velocity, but you have to do 7 first. You need to find the net torque. You need to find the moment of inertia. Look at that equation sheet in your book. And then you also need to find the rod's angular velocity, angular acceleration and velocity. While you are doing that, actually, I'm going to hand out this equation sheet. You'll need it for your quiz in about 15 minutes or so. First. Seven should be pretty easy, right? Why is it easy? Right, there's only one force that causes the torque. And so your torque for number 7 will be what? That's right. This one? Clear? The torque for number 7, the answer is 10. All right, we'll stop in about 15 or 20 seconds. Let's stop at 245. 245 is number 8. On there. Okay, good. B is right. So the first thing you need to do is find the torque. The torque is 10 Newton meters. Again, no torque from here and no torque from there. So your torque is just going to be 10 times 1. It's actually a negative 10 Newton meters, although at number 8 we don't use that. Now I want to find, I know that my torque is equal to 10 Newton meters. I need to find I. You look on your table and you'll find that the moment of inertia for a rod is 1/12 mv squared. And so that's going to be 1/12 of the mass, which is 3 times 2 squared. Oh, look at that. That's just equal to 1. So that's my moment of inertia. And then I can find alpha. So alpha is torque over I. That's from Newton's second law, 10 over 1. Those units are going to be radians per second squared. And then I want to find the angular velocity, omega equals omega naught plus alpha t. And that's going to be 0 plus 10 times 2, or 20 radians per second. Hey, why can't you ever hear pterodactyls going to the bathroom? Because the P is silent. All right, that's number 8. Good job. Let's try number 6. I want to try number 6. This is a conservation of angular momentum problem. You think about how this bar is changing, you can probably get rid of a lot of options right away. Thinking about, is this thing going to speed up or slow down based on what you're thinking about how it's changing? And if you're clever, you might be able to just think about how the relationships are related and not really get into the calculations at all. All right, let's stop at about 225, 225. Fortunately, on the next exam, you'll have a little more time because I'll still give you the full hour for the exam, but you'll have fewer questions. So you'll have a little bit more time, but you still want to be mindful of how much time you spend on a question. I'm going to pause this. All right, so I have this bar, and it extends. So I have a bar that's originally 3 meters, and then it extends to 6 meters. Is that thing going to speed up or slow down? It's going to slow down. So it originally starts at 2 revolutions per second, so I can get rid of those options. I know it's going to slow down just thinking about the figure skater or the dancer. When they put their arms out, that causes them to slow down. Or when you're on a merry-go-round and you're in the center spinning, and then you move out to the edge, that makes it slow down. It slows down quite a lot. So it is going to slow down to either 0.5 or 1. And to figure out how much it's going to slow down, I'll look at the conservation of angular momentum. I initial omega initial equals I final omega final. The only thing that's changing here is the way the mass is distributed. And I, for a bar, is equal to 1/12 mv squared. Now, the bar is going from 3 to 6 meters. That means that I'm doubling the length of the bar, which means that I'm quadrupling the moment of inertia, because it's squared, right? So b squared, if I double it, it's 4 times as much inertia. So going from I initial to IF, I get a factor of 4 right here. But I know that the momentum has to be conserved. So that means that omega final is going to be 1/4 of its original value, or 0.5 revolutions per second. That's the easiest way to approach this problem. There is a harder way, and that is I can just calculate I initial. That's 1/12 4 times 3 squared. I can calculate I final. That's 1/12 4 times 6 squared. This is 3. What is this? What's I final? Can I do that? 4. Bless you. That's 12. So I'm going from 3 to 12. So I have 3 times 2. That was my initial speed, equals 12 times omega final. And then that's going to be omega final is equal to 1/2. Let's see how y'all did on that. Okay, A is the right answer. B is the next best right answer, although it's wrong. The next best wrong answer. But it is slower than the original speed. It's definitely not going to speed up, and it's definitely not going to keep the same speed. Okay? That is conservation of angular momentum. Let's see if we have an energy problem. That'll probably be our last one. Find okay, let's just try this one. This one's an easy one, I think. I hope it's easy. Number 8, and that's exam 4, fall 18. Number 8, exam 4, fall 18. All right, we'll stop in about 10 seconds. Stop at 150. Guess if you're not sure. 150, going away. looks like we were sort of split. I think the answer is D, but let's see. So first of all, I need to recognize this is a hoop. Look on your equation sheet. I for a hoop is equal to mr squared. That's the same as the equation for discrete particles. Just turns out that's how it works out. So the hoop has a mass of 10, a radius of 2. So it has a moment of inertia of 40 kilogram-meters squared. And then it rolls at a speed of 4 meters per second. Oh, this was more complicated, actually. Yeah, so the speed is 4 meters per second. I know that v is equal to omega times r. So I say 4 is equal to omega times 2. So omega equals 2 radians per second. Then the rotational kinetic energy is going to be 1/2 I omega squared. That's 1/2 of 40 times 2 squared. That's 20 times 4 or 80 joules. However, this problem, or this object, also has not just rotational kinetic energy, but it also has translational kinetic energy. So I also have to consider that the kinetic energy of it moving in a straight line is 1/2 mv squared. So that's 1/2 of the mass, which is 10 kilograms, times the speed, which is 4 meters per second squared. So that's 5 times 16, and that's 80. And then the total energy is the sum of those, or D. Y'all did pretty well in that. We haven't really talked about that you can have a rolling body that has both rotational and translational kinetic energy. But it's true in the lesson, and you'll see that on the exam. You'll see it as you're practicing too. All right, we'll have another day on this. We'll work on it on the help session too. The help session will be sort of for the exam, and we'll be good to go. Let's get your quiz going. It's a shorter quiz. I made it a little shorter, so you don't need as much time. But this is green, right? Theorem green. I'll start your quick thing if you guys need a calculator. Okay. Okay. I do want to bring back.